Okay, so welcome back. We have our second session of the morning with two very interesting experimental talks. So the first talk of this session is from Manuel Endres.
Hi everyone. Sorry for the very uncreative title, but I'm just going to give an update on basically recent experiments in our group. Some published, some unpublished. And I, in the spirit, that's something new. In the spirit of the talks yesterday, I'll not have a lot of introduction. I'm just going to jump right in. So in our group, we trap alkaline earth atoms, specifically strontium. And they're typically used in optical clocks in lattices, and the reason is that they have very narrow optical transitions. For example, like this kind of clock transition or cooling line in strontium that's about 7 kilohertz, and you also have metastable states. So our goal originally was to kind of trap, strontium atoms in tweezers, and we did that successfully around 2018 with first imaging and narrow line cooling on these narrow transitions. We moved on to very high fidelity imaging. Some sort of in line with what Adam did, worked on tweezer clocks, really kind of stabilizing narrow lasers to atoms in tweezers, and then worked on a lot of high fidelity Rydberg excitation. So I should say that a lot of the work that we have been doing was inspired by the turbine quantum gas microscopes with a lot of imaging schemes and cooling schemes and so on. Actually, people in these quantum gas microscopes actually did before us. And of course, I should mention the work by Adam and Jeff that you heard about it yesterday.
Could you turn on your microphone?
Oh, sorry. That have a lot of work in parallel to what we are doing. So I won't cite everything explicitly, but you should. Oh, this is very loud, huh? You should expect that a lot of the things have been done by them as well. Let me jump right in. So this talk, I'd like to talk a little bit about can we push Rydberg fidelities more using alkaline earth atoms. And I'd also like to talk a little bit if we could get some qualitatively new features using this alkaline earth level structure. Okay, let me jump right in. So how does the Rydberg excitation work? So it's a little different than alkaline atoms. So we start in an absolute ground state and then move to this metastable state with a clock transition. And this state lives very long. And if you want to just do quantum simulation, for example, you could utilize this as an effective new ground state because it's much longer lived than the Rydberg lifetime, basically. And from there, you can go with a single photon transition to S-Rydberg states, and it's a relatively clean excitation pathway where you can go to very large Rabi frequency, extract decoherence from intermediate states. It's easy to get very cold, so all that kind of Doppler noise and so on should be reduced. We have new detection schemes using an ion core. For example, using auto-ionization detection, we can detect these Rydberg states with high fidelity. I don't have time to talk about this. And the Rydberg states are trappable in principle, and this is something that Jeff nicely showed in his work, for example. So this is some sort of data from our 2020 paper, just to kind of warm up a little bit. So if you drive Rabi oscillations at a large spacing, on resonance, you see some sort of textbook Rabi oscillations, and you can see some sort of about 50, 60 of those oscillations. If you do an echo pulse in between, it's actually more than 100. I don't have the data on here. So at that time, this was some sort of the first Rabi oscillations with alkaline earth atoms going to Rydberg states, and the pi pulse fidelities are about 99.5 or so without correcting for preparation and detection errors. We back in the day already showed that blockade oscillations and Bell pair generation in the ground to Rydberg manifold. So everyone knows about this in the audience. I don't have to explain it. So if you put the atoms very close by, you can drive to a superposition state on ground and Rydberg states. Again, ground here is our metastable state, and this is square root of 2 Rabi enhanced. And then at the time already, we saw a lot of these blockade oscillations. We had fidelities around 99 with spam correction. So I want to talk a little bit about what are these fidelities limited by, and want to present some of our new data that came out recently. And in particular, if we can, push them to some sort of a 99.9 and maybe even beyond regime. So can we do better in terms of Rydberg fidelities? And we knew for a while that we should be able to do a lot better. And I want to mention this explicitly. So we have these results that came out finally this year, and they're about many-body benchmarking. So we do experiments in there with up to kind of 28 qubits where we measure fidelities in very, very highly entangled regimes. And these fidelities, if you really look at them carefully, they're consistent with a fidelity for these Bell pairs above 99.9 actually. So in other words, they're actually inconsistent with anything below. So it would be very, very unlikely to get this to high fidelities with this. So we went back then with these insights and tried to actually measure this Bell pair fidelities and sort of with this insight and a few more insights and see if we can actually show this in experiment, basically. So at the same time, we were some sort of inspired by conversations with Jeff about erasure error conversion and also utilized this as part of this study. So let me kind of jump right in. This is some sort of the 2023 data on these blockade oscillations, basically, and you see they're very high contrast. And if you look very, very carefully, you find, for example, that at the time where you expect the Bell pair, you have a probability to be in this Rydberg ground plus ground Rydberg of about 99.86, and that's very high, and that's raw data at that point. And then you can actually return to the ground state with above 99.8 fidelity, so that's nice. Then using this lower bounding procedure that we also developed with Hannes actually back in the day in this Nature Physics paper, you can then put lower bounds on the Bell fidelity, so the raw fidelity is above 99.6. If you then correct for measurement errors, it's above 99.7, and then if you do spam correction, it's about like 99.85. And I would consider this one where you correct for measurement errors some sort of the Bell generation fidelity. That's the fidelity of the Bell pair in the experiment. And this was, you can call some sort of a process fidelity. Okay? So this shows that you can prepare two-qubit entangled states some sort of at the close to 10 to the minus 3 in fidelity level for neutral atoms. So now before Misha, makes his comment. Okay, so I asked DALI to some sort of generate this image. And they took it very seriously, actually. If you look carefully, they took the gate input. So, okay. Just, okay, it's just a Bell state. Okay, good. I'll show you this in confidentiality.
You also type post-selection?
I can talk about post-selection, actually. It's okay. It's okay.
It's a good try, but it doesn't make it,
What do you mean? Well, we can talk about the post-selection. Well, let's talk about it. Okay. So how did we get to this value? So that's some sort of, I think the biggest improvement has nothing to do with post-selection. The biggest improvement actually has to do with finite blockade energy. So back in the day, our data was actually limited by finite blockade interaction. So what you see is the Bell fidelities of multiple data points as a function of basically the blockade energy divided by omega. And there's some theory line here that you can just derive from perturbation theory, basically. And you see that back in the day, even if we had tried harder with like noise and so forth, we wouldn't have been able to actually go higher. It has to do with some sort of admixtures from non-blockade, from blockade violating states, basically. And what you see then in addition are some sort of a bunch of curves. So there's basically an error model simulation for the lower bound and error model simulation for the true fidelity. There's a kind of black and gray line. So this is some sort of actually the biggest jump in there. Plus we learned a lot how to align these beams and did a bit of work on like noise in amplitude noise. And then in terms of the total budget you have then at this high blockade energy, it looks a bit like this. So there's some sort of still a limit in this like bare Bell generation pulse that you get from finite interactions, but that limit is very high at this close distances. This is now about 2.5 micron distance. And then you can go through this error budget and first compare some sort of the total fidelity that you predict in your error budget with the experimental fidelity, and they match very, very nicely in terms of the lower bound. And you also see that this model predicts that the lower bound is actually quite a bit worse than the true fidelity. And this has to do with the fact that this lower bound is effectively the fidelity at applying the operation twice. So there's some sort of almost like a square root you have to take to kind of really get the right fidelity. But we usually just quote the lower bound. But just as an FYI, that these lower bounds, they actually underestimate the fidelity quite a bit. So that's some sort of the point. Okay, so this really kind of implies that an experiment actually, even if you have 99.7, 99.8, it's truly actually 99.9.
There's no Rydberg lifetime in that area?
There's Rydberg lifetime. This is the Rydberg lifetime. Let me kind of talk about this briefly. So this is, so like first of all, let me say that I think we understand our errors down to the 10 to the minus 3, even lower regime, both from these experiments and also from all these many-body experiments that we did. And now at this fidelity level, some sort of the dominating effects here, you can see there's some laser noise in here. Okay, so this is this, and then here the most dominating one is actually AC laser noise. And in our case, we don't do cavity filtering, for example, yet. So for example, if we did that, this one would be a lot better. And then there's Rydberg state decay is actually at this point, and this is what we call dark state decay. Let me come back to this. Sort of, I think what we see now, and this is, I think, interesting. So first of all, we understand it, and then we're also at the level where some sort of laser noise has become comparable to the intrinsic decoherence in the systems, and that's something I think that's nice to see. Okay, the other thing we have been doing, and this is what Misha wants to complain about, is our erasure-conversion and excitation schemes. So what we do is we utilize the alkaline earth level schemes, in particular the existence of dark states.
I'm not complaining.
No, I'll say.
Just say.
We'll talk about it. We'll be honest, don't worry. So the idea is very similar to what Jeff explained. So you basically can have a qubit subspace. In our case, this is G to R. Okay, so this metastable state. And then you can have leakage out of this qubit subspace. And this leakage can partially go down to the absolute ground state, and you can repump some of the metastable states. And then you can try to do an image here to detect these leakage errors with spatial resolution and single atom resolution. That's what we're doing here. So we're doing a fast imaging scheme on the 461 line, and we can image single atoms in about like 20 microseconds. We have shown also 99 fidelity, but what's in the paper is 98 fidelity with larger arrays actually. And so that's good. So the idea here is that you can detect these images without perturbing at least the population in these states. I'll come back to coherence in a second actually. Okay? So sort of the idea is you do this Bell pair generation, just put the Bell pairs, apply your unitary to generate the Bell pairs, and then we do auto-ionization of the Rydberg states, do the erasure error detection in here, and then we do a final detection image. And now the key in this erasure error schemes is that you have separate images. I think I want to highlight this a few more times. So you have separate information. It's completely separate from your final detection that you can use. And it's a bit similar to saying you take data over the weekend, say from Friday to Sunday, and then Saturday afternoon your AC breaks, say it goes 20 degrees high. As additional information you have, you would probably throw out your data. That's some sort of a same sort of idea. You would know you for sure made an error. That's some sort of the thing. So it's a post-selection scheme that we use, and the post-selection is applied to additional information that you didn't have if you didn't do this. And that's, I think, the key. There's another issue in here that needs to be discussed. I'll come back to this, is the question of coherence preservation. This is what Jeff calls mid-circuit erasure, and I'll come back to this a little bit. So this is not yet mid-circuit erasure. I think I want to be 100% clear. But anyway, we can use this information and then throw out basically pairs where we saw an error. That's what we do here. Okay. So we have an additional erasure image that gives us the location of the errors, and then we can excise pairs. So excising means you just take out the data, basically, where you saw an error. Okay? And this helps with the raw fidelities a lot. So this is some sort of the bare fidelity, and also helps you with the measurement corrected fidelity a bit. And it doesn't help you too much actually with the spam corrected fidelity. So sort of it's all within error bars whether or not we don't do that. And it has to do with the fact that the way this is done here actually mostly catches preparation errors. So we have some sort of do assembly, then we do this clock pulse, and after the assembly and the clock pulse, there's a bunch of atoms still in the ground state, basically. And these ground state atoms, they go through all of the schemes, they're detected here, and we basically throw them out. So in a sense, there's some sort of a selection on preparing the pairs correctly. So we actually don't really see Rydberg errors in there and can never see this within our error bars. So they're actually very, very small. So the effect from catching some sort of a Rydberg array, a Rydberg error for this Bell pair generation is some sort of a 10 to the minus 4 effect, actually. So it's sort of mostly corrected for preparation error via this erasure detection. Okay, is it clear? Good. So can you see the Rydberg decay?
The Rydberg decay was a larger fraction than 10 to the minus 4 of your error budget, wasn't it?
No.
Just the fraction of those errors caused.
Yeah, so this is, okay, let me kind of be clear. So that what's left in here is what we call dark state decay. So I'll come back to this in a second. So there's decay from Rydberg that we see and decay from Rydberg that we don't see. The leftover decay from Rydberg that we don't see is this bar, what we call dark state decay. And the one that we see is some sort of included in the error model. So the error model does erasure correction itself, basically.
So this is after you take out the...
Yeah. And then in the model, you can some sort of take the one that you see into account or out of account, and then you see it's a very, very small effect. Actually, it's 10 to the minus 4. And it's kind of correct, yes. It's like a little higher than 10 to the minus 4. So this is about like a 2 or 3 10 to the minus 4, and the other one is 1.4 10 to the minus 4. So it's about a third that we see. Clear? Okay. So it is post-selected, but I think I want to really highlight this is different than post-selecting on a final image, because if you post-select on a final image, you didn't know that you made an error. Here you know you made an error, and it's the same whether your AC goes out of control. You also know that probably you made an error with high probability. Okay, that's sort of the logic. Okay, so can we see that the Rydberg decay erasure? So it's what Chef did, and if I understand this correctly, he kind of like slowed down his experiment a little bit to actually see them. And the point here is that, first of all, you don't have a lot of atoms, and the experiment is very, very fast. So we have like 5, 6, 7 megahertz Rabi frequency. So it's an extremely short pulse. So it's very, very hard to detect. So what we did to really kind of amplify this, we went to a quantum simulation experiment that's first of all slower and has a lot more qubits. Okay. Okay. So can we see the erasure from Rydberg decay? And to this end, we went basically to sort of prototypical quantum simulation experiment, some sort of following like the pioneering work from Harvard at the time. And we basically just did an adiabatic preparation of a C2 state. Okay. So we made a sweep. And then in this sweep, we did 2 erasure images. So we did an image before we do the quantum simulation and an image after, where we look at this, we call it decay erasure. And then we have the final measurement. So there's now essentially 4 images, one for the preparation in the atom by atom assembly. Then there's a preparation erasure image. Then there's a decay erasure image and a final measurement image. So there's actually 4 independent images. So just to kind of go into the details, so this is the sweep. It's basically just some ramp of the tuning and amplitude to go into the C2 phase. And then you can look at this erasure probability that you find errors in these images as a function of time. And you see this preparation error, it basically stays constant, while this Rydberg decay erasure actually grows with time and actually matters some sort of our model understanding. Okay, so we see Rydberg and decay erasures basically separately, but some sort of amplified in a larger system and slowing down the dynamics. So these are really the fact that this grows. And matches some sort of our understanding, some sort of proof of principle for that.
Should I understand this as basically the probability of an erasure in either the preparation or the decay at the last time here is like 45%? Like
and there's many atoms. I'll come back to this in a second. It's pretty aggressively like taken out.
So
I'll come back to this.
But 0.45 to the 26 is the fraction that.
No, this is a total fraction. The total in the total array.
Okay.
Because we could take, maybe we should show it with a single, it's the total array in 26 qubits. I'll come back to this. You can actually adjust the fraction. Okay, clear? Okay, so we see the Rydberg decay. And then you can check, for example, that's some sort of an exercise just to see the effect, because it's not obvious, for example, in a many-body, so okay, you see an error, but like, does it even have an effect on what you want to see? Okay. And here, for example, we plot the probability to land in this AFM states. As a function of the tuning, and you see, so at the phase transition, a very sharp increase of this probability, and then you see an improvement from just taking out these preparation errors, for example, and then you see an improvement again when you take out the decay errors. Okay, so you see actually the quantum simulation results become cleaner. Okay, that's some sort of the proof of principle. And also your slope, if you take the derivative here, which has a peak pretty close to the phase transition, also improves with this kind of excision of these erasure errors. Okay, so I think now I want to come to the part that I found most interesting in this, which is like, can you somehow learn more about the effect of these errors? Because now I have more images and I have a lot more data actually that I have been using before. So can we really see if, for example, these errors have measurably different effects on the many-body dynamics in here? Okay, that's sort of what I want to get at. Before I get there, I want to introduce another concept here, which is AFM probabilities, because I'm going to need it to understand this error effects. Okay, so you can ask, before we look at this, at the probability to find a certain AFM magnetization. So what do I mean? AFM magnetization, you can just write out an operator that's a sum of sigma c with a -1 to the power of j, some sort of a staggered magnetization operator, and that's a operator that has about n eigenvalues, so it's a somewhat high order observable, and you can look at the probability to find a certain eigenvalue in the system. So you basically just look at your images, you count the number, and you do this many, many times, create a histogram, and then these are the histograms I'm plotting in some sort of a 2D plot as a function of the tuning and this magnetization operator. So the way it's defined, it can go both +1 to -1. If it's +1, it's one staggered magnetization. If it's -1, it's the other staggered magnetization. Okay? So you see that in the disordered phase, there's only one peak, and then once you enter the order phase, you actually see 2 peaks. These are the opposite AFM orders. And it's a very clear signature of spontaneous symmetry breaking actually in these systems. So here's some sort of what you see actually in the deep phase. You see basically the 2 peaks of the 2 AFM orders. And at the phase transition, it's actually a very flat distribution. So this flat distribution at the phase transition is very non-trivial. I don't want to talk about it too much, but that's actually universal as far as we know. And you see some sort of the peak from no magnetization to these kind of 2 AFM orders, the change. You see this very clearly. And you also see now a little bit what the effect is from some sort of excising this error. So if you don't excise them, they somehow pollute into different AFM orders. So that's one effect. I want to make a comment here. So what we do in this data is actually an inverted sweep profile. So this is actually different from what has been done in Harvard back in the day. So we actually go the other way around, and this effectively, without going into details, quite similar to what Paris did in this XY model, actually prepares attractive model. Some sort of, this is this very old idea for Bell states, we had at the time. And in this attractive model, the ground state on an even chain is actually a true GHZ state down here. That's what you would expect. We didn't measure the coherence, just to be clear, but it's a true GHZ state. And it's in open boundary conditions. I disagree a little bit with what Kankwen said. It's possible in open boundary conditions to see clear C2 symmetry breaking. Okay, this is some sort of very clear signature. Okay. So this is different because if it's repulsive, you wouldn't actually get that. And if you make the chain even odd, it also doesn't work. Okay, so there's one specific condition where this works. And it's a bit in analogy to the GHD work from Misha's group. There is an odd chain repulsive. You wouldn't get this, but if you modify the boundaries the right way, you also get clear and clean C2 breaking. It's actually, in fact, in that paper if you kind of some sort of interpret it that way. Okay? Good, so this is AFM, GHZ state, not GHZ state preparation, but C2 symmetry breaking. Now, I want to ask, so do the preparation and Rydberg errors actually have different measurable effects? And that's some sort of actually my favorite part. So again, you have these 4 images, and they're completely independent. And then if you do this experiment, sometimes you see a preparation error, sometimes you see TKA, and then you have this sort of your final detection. And then you can do some sort of games that are quite nice. You can basically correlate the errors with your final readout. So for example, you can look at the conditional probability to see a certain pattern of Rydberg excitations. This is what's some sort of plotted here as a function of distance to the error. Okay, so first of all, you have a plot where you had no error. This is actually completely flat because everything kind of washes out. We average also over the position of the error. But once you have a preparation error, you actually see that close to this preparation error, actually a Rydberg excitation is pinned. So the color scheme here is such that when you see this light color, it's actually Rydberg, and when red is actually ground state. Okay? So you see there's a Rydberg excitation pinned, and then next to it a whole AFM order, basically, that kind of extends out of it. Okay? And you see this on both sides of the error. Okay? Some sort of, and the reason for this is that if you have a preparation error, say you have a chain of 26 and there's an atom missing in the middle, you have like 2 chains, it's 26 minus 1 is 25, and then depending on where the error is, the 25 is split into 2 chains, okay? And the 2 independent chains, now they're odd, they can have some sort of a pinned order that you see, some sort of, it basically pins the order, okay, the effect. Now if you look at a Rydberg decay, it looks a little different. It looks almost like it pins the order some sort of in these early times, and at late times, if you look very, very carefully, you would see that there might still be an order, but it's actually shifted by 1, and it's a little bit curious. So we looked at this more carefully. So what you can do is you can basically define this AFM operator relative to the error. So you can basically, which is AB sublattice, depends on where the error is found, okay? And then you can just plot the average. So this average of the AFM magnetization, if you do not look at the erasures, would kind of be 0, because it's basically the average over this histogram. Okay, this is what it is. But now if you pin it, with a erasure error that you see, you can first look at the decay, the preparation error, which is this yellow curve. In case it kind of starts at 0, and then it pins it very clearly in one direction, and some sort of the pattern that you see here. And this basically pins such that Rydberg starts next to the error. Okay. Now, if you look at the Rydberg erasure error, you correlate with the Rydberg, you see that it first seems to pin in this one direction like a preparation error, but then it goes into the other direction. It's clearly out of error bar with 0 actually at the end. Okay. And it has some sort of, obviously some sort of a different effect depending on which phase of the system you are in. And it's actually easy to understand, but I find it kind of nice. So in the disordered phase, when the Rydberg decay happens very, very early, it basically looks like a loss. Okay, so you basically have a hole in the system and it looks like a preparation error and it does the same pinning. But now in this ordered phase, where you expect some sort of this GHZ states or a mixture, it doesn't really matter for what I want to say. So you have some sort of both ordered patterns in it. The Rydberg error actually kind of measures which one you have. So it's like if you're in this state and I have a Rydberg erasure, I know that at this point, for example, I had a Rydberg atom. Okay, so I gain additional knowledge. And that knowledge tells me if I add the state before that the neighboring atom has to be ground now, not Rydberg. So it pins again in order, but for a completely different reason, because it actually measures which of the AFM states you have. Okay, some sort of, that's a bit non-trivial, I have to say. So when you see this here, so one, it pins like the Rydberg next to it, and then it pins like a ground state next to it. And that's some sort of this transition that you see. And that's some sort of, I think, quite non-trivial actually in terms of understanding the errors. Okay.
Sorry, no.
Yeah.
But you don't know at which time this error actually.
We don't know, but that's right. But it's more likely if you go later that it happened later. It's integrated actually. In fact, that's right. It would be cooler if you could time resolve it. I agree.
So that's why you only get a little bit of uncertainty.
Yeah, right. It would be some sort of, it's the integrated, some sort of probability for seeing this some sort of times, and it carries a little bit from the early time with it.
My other question is, the ones that you see are what you call bright decays,
Yeah.
which are not decays to other Rydberg states.
Mm-hmm.
Those you might expect to behave quite differently.
Right, and we did not look into this carefully in this work, but you could probably like kick them out and look at the final data then post-selected on this, and for example check if there's some nonlinear effects and stuff like
But
this.
you think you just don't see those, like when you condition on these decay erasures.
But by definition, we call the ones where we see it bright. I'm not sure. So this is the definition of what we call it. Is it clear? Any questions on that? Okay. So let me kind of do a few conceptual points before I go to the next topic. So how should we think about excising these shots with erasure errors? There's two different things that we do here. We excise errors from preparation, and this is strictly speaking heralding in a way. So you basically herald the system on having an atom in the right state before you go and do your experiment, and that's okay. The one on the decay error is a little bit more subtle. So this is something we discussed quite a bit with Hannes, who kind of helped us to understand this. It's basically monitored quantum dynamics, because if you imagine you had only Rydberg decay and you would detect a full channel, okay, so only error. Normally you would write down a master equation or quantum trajectory approach. And then if you do this, if you can detect all of them, you would actually select on the trajectories where you never had a jump. And in the quantum trajectory language, it would mean that you actually evolve on a non-Hermitian Hamiltonian that still has an imaginary part in it that comes from the champ. So there's a minus I gamma, C dagger C for the kind of experts, open system dynamics. So in essence, this is actually, in the way this is some sort of designed here, is actually monitored quantum many-body dynamics. And I think this is actually quite a...
So the fact that the dynamics are non-Hermitian isn't a result of the measurement. It's the fact that you can detect which trajectories occurred based on the measurement, and therefore can model. Okay,
so the dynamics is anyway non-Hermitian. If you have errors in some sort of a non-Hermitian Hamiltonian, you can think about it with sort of staggered with jumps. But if you can, it's like a two-level system that, Misha has it in his quantum optics script. It's basically this with many bodies. So you have a two-level system, so you can detect all the spontaneous emission photons, and then you select only on the runs where you never detected anything, and you want to describe the dynamics, say, on the drive. And then you would have to some sort of describe it with a non-Hermitian Hamiltonian, that part. But if you take all shots into account, you would describe it by master equation, which is solved by non-Hermitian Hamiltonian plus jumps.
Right, so yes, I
some sort of my point is a little bit that if you excise these Rydberg errors, they're not completely gone. They're still somehow there because they appear as a non-Hermitian term in the Hamiltonian.
I agree with that.
That's some sort of the point.
You have both of these things going on in the quantum simulation, but by virtue of being able to post-select on which trajectories you observe, you can ensure that you're only seeing the non-Hermitian.
Exactly, that's the right formulation. Yeah, that's right. So you kick out the jumps, but the non-Hermitian part is still there. Okay. Let me kind of make another point, which is how many shots do we throw away, coming to your point. And this is something that you decide, and that's also very important. So I can decide not to throw out anything, but just taking all the shots into account. But then I can put my detection threshold differently. So I can say, okay, I put it very, very high that even when I have a lot of photons coming from these errors, I take them into account. And this is some sort of done in this graph, where we change the detection threshold, and this basically changes how many of these shots you basically some sort of excise. Okay. Or it doesn't, it changes how many you excise, which is the x-axis here, and then the y-axis is the final result, is for example the C2 probability as a function of how many shots you throw away. And you see there's some sort of an optimum probably where you kind of don't throw away too many shots, but you still kind of reached already some sort of the best result. So this is some sort of a trade-off between improved results versus effective runtime, right? So because like if I throw out shots, I have to just do it many more often, okay? And then, what, 3 minutes left? Until 30 or?
Yeah.
Until 30, okay, cool. So, right, good. It's a trade-off between improved results and effective runtime, and it's under your control. So you can decide to do that or not, and you can learn something from it. It matters most, I think, when you have classical costs to simulate what you're doing that scales non-linearly with the fidelity that you have. And there's actually cases like this when you do high entanglement dynamics, or certain cases where there's actually very non-linear, even exponential actually. There, you would want to do that. You increase your fidelity, it makes it harder classically, but you lose only linearly in the time. Some sort of, you want to do quantum advantage experiments, something like Google style, you would actually gain, I think, with this stuff. Okay, and additionally, we can gain no insights into errors. Do we preserve coherence? I want to make a quick comment on that. So we don't use it in that paper, but we do, in fact. So this ground Rydberg coherence is not affected by the imaging light, as you would expect. However, the lifetime we have for the Rydberg states is not a lot longer than the imaging time that we have. So in fact, it's some sort of useless in that point, but it is, in principle, coherence preserving. And you have basically two solutions there. Either you go to much longer lived states, kind of what Jeff showed, nuclear qubits, and I'm going to show you, if I have maybe 10 more minutes left, something in motional states, or you could improve the imaging speed, make the imaging a lot faster. Okay. Okay, so just to go for intermediate summary before I go on my run for motional stuff. So we demonstrated erasure conversion is basically the localized detection of errors. We utilized it for NISQ devices. We find now Bell state fidelities in a kind of 99 regime, and we understand the errors very well. And there's a few new avenues you could think. It's not inconceivable to go to 4 nines, I think, if you maybe improve on the laser noise. And you could also even put these things into cryo to kind of get rid of the black body. I think there's some sort of not totally gone. And then, of course, this erasure conversion, it helps you with error correction thresholds, which is, of course, very nicely some sort of proposed in Jeff's work. And what I want to briefly talk about is erasure conversion for motional states, if I have 5 more minutes, actually. So, questions on this stuff? Before I ask questions, we can discussion now. It's good? Okay, good. So let me kind of briefly talk about this. So there's something I like a lot because it's conceptually a little bit different. So can we use motional states and tweezers as quantum information carriers? And then to this end, you need to ground state them. So we have been asking. And what I wanted to do for a while now is like somehow can we extend atom by atom assembly such that it also effectively cools, and that's some sort of the bottleneck here. So the idea is you have tweezers, particles in a thermal state, and then we use sideband driving then to convert excitations into differences in electronic states. Some sort of it's relatively simple. You basically do a blue sideband drive. If you in an emotionally excited atom, you go back to the ground state. If you're in the ground state, you're blocked. Okay, so that basically maps the emotional excitation into some sort of a collar. The collar is just in which of these electronic states are you. So now if you're able to read out the electronic states such that the emotional ground states are unperturbed, you will see locally where you had emotional excitation. So this is the logic. And this in essence, erasure detection. So you basically erasure convert motional excitations to local errors that you can see. And then if you image them, you want to image them such that the tweezers where you didn't have an error are unperturbed. That's the logic. So this is some sort of the idea. And again, it's important that you don't perturb the other one. So some sort of here's the final kind of results how we do this. Again, you start with some sort of Sisyphus cooling. You have a first picture. You have some sort of motional excitation. And I'm just going to call it spin now, the clock transition, grounded and excited state. We do this motion spin conversion where we basically convert emotional excitations into collars. So all the excited motional states are now red. And then you can detect the red ones with this fast imaging scheme or even with slow imaging in this case. And you see these are the atoms where I had emotional excitation. Okay, and now you can do error correction, classical error correction in this case, and you can try to get rid of those. And then there's basically 2 versions of this that we did. One is replacement, and it's basically atom by atom rearrangement. So if you have more atoms, I can take them out and move ground state atoms in where I know I had them. And I know the atoms are there because I did atom by atom arrangement before. So I know they're there. I detect the hot ones, and the ones that I didn't see, I know there's an atom in the ground state. That's some sort of the logic. And I can base this basically then build atom by atom an array of ground state cooled atoms, some sort of the logic. Okay, so you can also do a reset cooling, so you can do some site selective cooling. If I have time, I'll talk about this. Anyway, this is some sort of the bare results. You can have, in our case, we have an initial ground state probability, motional of about 77%. And then with these 2 different cooling schemes, we get to 93. And this replacement is actually the most effective in going cold. We reach about 98 for Okay, so proof of principle for what we call sort of erasure election cooling or Maxwell cooling, whatever you want to call it. And it's basically like atom by atom assembly, but it's selective to motional ground state atoms. Some sort of, that's the logic. Okay. How cold can you get? Is this better than sideband cooling? It turns out it beats actually sideband cooling generically. So this is some sort of the results from this replacement cooling. And this is some sort of idealized sideband cooling. So you take sideband cooling and you make as many assumptions as you want to make it better and better. Basically, for example, no laser noise, no line burst, nothing. And it turns out that basically this erasure replacement cooling beats sideband cooling in principle for all trap frequencies and lambda decay parameters. And in practice, with the noise that we have in the experiment, it even beats the idealized version for low trap frequencies. So we get actually to pretty high ground state probabilities even at very, very low trap frequencies and very, very bad lambda decay parameters. Actually, that's kind of remarkable, I think. Okay. And it's basically measurement and feedback cooling that can be better than normal laser cooling. Maybe it's not super surprising, but it's maybe a little bit surprising because they both utilize sideband transitions, actually. Okay. It's kind of like evaporative cooling, so you throw away atoms, right, that are hot, and the rest kind of rethermalizes, but they don't rethermalize here, but they resort. It's the kind of sort of that analogy. Okay. Let me skip this. The selective cooling uses single side control. Maybe some people read that paper. We do single side control now by moving tweezers actually in laser fields. So there's some sort of a simple method to do that. It doesn't utilize tracing beams. Okay. I want to go briefly to this final question. So can we utilize motion now as quantum information carriers? So that's what I wanted to get at. And I want to show two things. One is mid-circuit detection, and one is motional entanglement. So you can coherently shelve the spin state, which is electronic transition, into the motion. And it's relatively simple to show. You make a superposition state on the spin and just map it with a blue sideband into a motional superposition state. And then you see, for example, this coherence oscillation. In the superposition phase, in these motional states, it basically oscillates with the oscillator frequency. That's what you see. It's basically Ramsey on the oscillator states that's shown here. And it's also independent of certain phases. For example, in here, it's independent of the laser phase that you use, which is good. And now you can use it, for example, for mid-circuit readout in a relatively simple fashion. So you have some sort of your erasure-cooled atoms, and you can locally shelve, for example, the superposition state into a motional state in the excited state, and then locally read out these guys without perturbing these, hopefully. And you have some additional image in here, and then you can unshelve it and come back. Some sort of the question here is like, okay, can I take these guys without killing those? And it works. Again, we do this fast imaging scheme. You see, for example, that some sort of basically Ramsey we see on these on the shelved atoms has some sort of a high contrast, and you can even do a little bit of erasure excision. So it's here you have information of whether or not you put them up, for example. And this is actually truly a mid-circuit erasure, actually, in the kind of notion that Jeff used. So there's a demonstration of mid-circuit readout where motional shelving is also mid-circuit erasure, actually, this figure. Interestingly, I was a little surprised when I saw this first. If you look at the coherence time of these motional states, like while you shelve, it's remarkably long. Actually, we see 100 milliseconds without doing much. One echo pulse, and that's it. So there's no dynamical decoupling, nothing. It's not maybe super surprising if you look at Martin's work. He has a nice work where he looks at motional superposition states. He actually saw multiple seconds, actually. And the reason is that these motional superposition states, they only care about trap frequency fluctuations. They're insensitive to magnetic field noise, anything, basically. So it could be a very long storage in principle. Okay. The shelving is some sort of useful for many different things. So, for example, you could entangle your atoms in a spin state, and then I need to stop there. Entangle your atoms in the spin state, and then map it into a motional state. So that's what we did. So we actually did Rydberg gates on the clock. Some sort of what Adam did basically a year or two ago, and then mapped the clock bell pairs into motional bell pairs. So that's sort of what's shown here. So you can basically just convert them. And this is the parity oscillation on the motion. It's a factor of 2 faster now, so that's good. So it's actually the state that we have has twice the trapping frequency. And again, the Bell state fidelity is very long lived. Some sort of, and just to be clear, this is a superposition state of both atoms being in a ground motional state and both atoms in the excited motional states. And it's, to my knowledge, the first demonstration of motional entanglement with neutral atoms, and more, to my knowledge, and has been done with ions only, I think, this kind of stuff. Okay, so you can do something that's called hyper-entanglement, where you entangle both motion and spin. It's kind of funky, actually, because you can do the motional entanglement and then apply a gate again to the spin. And what you generate then is a bell pair. It's a double bell pair. So it's a bell pair in the motion tensor, a bell pair in the spin, actually. So it encodes 2 bell pairs in one atom, which is kind of surprising that it's possible, but maybe not once you think about it, because they're independent degrees of freedom. And it's actually different from a qubit, I want to be clear. It's not a qubit. There are 2 independent degrees of freedom, and I have a Bell pair in both of those. Okay. It's a tensor product, and we show basically that we have that, just to get this sort of proof of principle. Okay, so with this I want to summarize. We showed this kind of erasure conversion, high fidelity Bell pairs. We have this kind of new stuff that some sort of will come out probably next week or in 2 weeks on controlling basically motional degrees of freedom. I didn't really have a lot of time to talk about the side resolve control. Did not have time to talk about the dark state enhanced loading we just published. I want to give like one update on this many-body stuff, which I like. So we have been working on probing many-body dynamics with up to 60 atoms for a while now, and we're about to write this up now. And there we had some sort of a recent breakthrough where we figured out how to actually measure mixed state entanglement in these experiments. And I like this a lot. So with experiments with up to 60 atoms, which has some sort of effective Hilbert space size of 2 to the 40 something. And this mixed state entanglement measure turns out to be some sort of super robust and works sort of for all experiments if you know the details of the experiment very well. And then you can put all of these experiments on the same some sort of graph, and you see that in terms of mixed state entanglement, for example, the experiments we did, they're actually on par to this Google Sycamore experiments where they did the quantum supremacy claim. Okay. They put something out recently which is a little higher, but they're on par. And they're higher than all these Quantinum and IQM results, actually. And this mixed state entanglement is constructed also in such a way that this is some sort of a proxy for the classical cost. So we know. So for example, this is actually, once this goes up, the classical cost actually also goes up. Okay, so I want to thank all the people in the lab. Strontium, we're also building a cesium machine if you're interested, and a theory collaborator. So this is what I'd like to thank you for your attention.
Okay, we have time maybe for a couple more questions.
Yeah, so regarding the cooling, the rearrangement sort of cooling, do you have a sense for what temperature you need the initial atoms to be so that you're not throwing away so many atoms?
It's very simple. You throw away whatever is not in the ground state with the replacement cooling. But you could do this, sometimes we do both. So sometimes we do the site selective recooling. So you basically the ones that are, you see, you recool, and then with single site control, you put them back into the clock state, you can start again. So it could replace like any, you don't need laser cooling at all, only to start and get somewhat cold in principle.
I see. And do you see this being done, like can it be done in alkali atoms, or do you really need this narrow line?
I think so. You just need a Raman, you just need a sideband resolved transition. And like it's, I think it's pretty general actually. And it's remarkably robust, so we never really some sort of optimized this thing. It just works basically.
Question from the balcony.
Yeah, thank you. So I have a conceptual question. If you put every atoms in the first motion excited state,
yeah,
and then do the quantum dynamics, quantum simulation of the spin degrees of freedom,
yeah.
then is it the same Hamiltonian or different Hamiltonian? And do you think you can maintain the coherent quantum evolution?
For what? For the motion?
The motions are just deterministically in the first excited state. Now we talk about the dynamics of the spins. Is that essentially the same? Just the
the spin dynamics is largely independent of the motional dynamics, which you actually see in this hyper-entanglement. That's the only way it worked, because in ions you couldn't do this so easily. This is completely independent, and this thing wouldn't work if they would like correlate, because you would get some sort of crosstalk. Huh? Say again? You could use them as many body levels. Yes. You could use them as a qubit basically, or bosonic degree of freedom, kind of Shulkerf style.
You can make two-qubit stuff.
You can do it too?
Two qubits.
Yeah, you could do stuff like this. Yeah, that's right.
Okay, last question.
Oh, you see, I see what you're saying. I see what you're saying. If you put them in a superposition state, you could do this interference. That would be interesting. I agree.
But you need higher fidelity than this.
Yeah, this is some sort of first try, more or less. Yeah.
Are you doing the clock for the cooling in all 3 directions?
The motional stuff we don't.
So this is 1D cooling?
Yeah, we do 1D. You could. There's nothing that prevents you from that. And this is only in 1D so far. But all of these results where we do the entanglement and shelving is one direction is cold and the other ones are kind of hot with like reasonably cold.
And then the other question was, are you able to, do you know like what the cooling rate is? Like how long does it take to do this?
Yeah, it takes an image. It's actually quite fast, because you only for this, especially this replacement cooling that we use, because you just take a fast image, and then you need to read it out. So actually limited by the readout speed. It would be some sort of 6
I'm only asking because one of the benefits of sideband cooling is that it's fast compared to heating rates that you might have. So I'm curious, like, to what extent.
Yeah, so it's limited. Yeah, so this is limited in the end by the like hold time, where you heat a little bit, and then the shift. If you read out the image faster, you would gain, and if you could do the shifts better, you would gain. But like some sort of the fundamental limits are different than sideband cooling. That's what I'm saying. So sort of if we compare them on the same footing, it's actually better. It can be better if you're good at some sort of preserving some sort of the motional state while you do that. And it has to do with, I can go through the details. So there's certain some sort of error sources in the sideband cooling that don't appear here actually. That's sort of the point. That's some sort of a hypothetical thing, but like in practice we see that it's better than whatever you could do with sideband cooling with the same Rabi frequency.
Okay, let's
Yeah.
come on again.